Yeah, very excited. I'm going to be talking about a work that I actually haven't shown before. So let's see how that goes. But I'm going to first build a little bit of momentum towards, motivating this particular work, which goes from perception, prediction, as well as motion planning. And hopefully this works. Cool. So first, let me build a 30 seconds introduction, about how self-driving works, which I'm sure that you have seen by now quite a few talks in this workshop, but I think it never hurts. But basically, every vehicle senses the environment. This is illustrated here with a LiDAR scene from the top. Then typically what you see is that you localize with precision for a few centimeters such that you can use your high definition maps. Then the next thing that the systems do is that they perceive the world around them. Then they predict how the different vehicles and actors are going to be moving in the next few seconds. And then we use this information about the past, the present, and the future in order to plan a safe maneuver towards your goal. And then you basically repeat this process every fraction of a second, and then you use control to make sure that what you intended to execute is actually what the vehicle is doing. Right, so in a nutshell, this is sort of a rough description of how a self-driving system works. Now, when we started working in industry and in this domain, the first thing that we realized is that in a traditional software stack, these are treated as very separate modules with very small interfaces between them. And there is actually a lot of reasons why that's not necessarily a good idea. And so the first set of systems that we built was we actually joined the perception and prediction into a single system, right? And such that you can share computation, you can end up with, you can propagate uncertainty, and you end up with a much better sort of both perception and prediction performance. And so this is back almost 4 years now. But the basic idea was that you can use your LiDAR data. We love bird's eye view representations, as Wolfgang said before. You can use a network to learn some interesting representations and basically detect where the objects of interest are and regress the trajectory of those objects into the future. Okay, and this is the perception system, and this is the prediction system, right? And in this way, you can utilize all the power of deep learning to do this with a single network. So it turns out that this simple idea works extremely well, and this is what I'm showing you here. Where in a fraction of a second, typically between 20 to 30 milliseconds, you can do perception and prediction, including tracking. So what you're observing here is we are detecting and predicting different objects in the scene. Prediction is seen with these dots that basically represent the most likely trajectory into the future. And the fact that the vehicles have consistent the same color across time, it means that automatically the system can actually track them as well. Okay, so this, coming back 4 years ago, this was actually a big step towards what is modern, self-driving systems. Now, if we step back for a second and think about, from that very simplistic system to what is the task that we really need to solve, and we look at what are the main difficulties when we're trying to do both perception, prediction, as well as motion planning. There is really, three key challenges. On one side, if you think about the scene around you and you look at every single, say, actor, it's actually the future might unroll in many different ways, and is impossible oftentimes to actually know what is the most likely trajectory, or what is the the trajectory that a particular actor is gonna do. So one simple example is shown here, where we have a vehicle, and we have no evidence into whether this vehicle is gonna turn or is gonna just continue straight, right? So we need to build systems that inherently are able to model this multimodality of the task at hand. The second key challenge in prediction systems is the fact that, well, every actor is not really independent, right? If you look at traffic scenes or scenarios, there is a lot of interactions between the different actors. And what is more important is not just about interactions, it's the fact that one interaction might trigger a chain of changes in behavior across the whole scene, right? So there's long-range dependencies this way. So modeling these interactions is something that is very important and it's difficult. So I'm illustrating maybe this with a very simple example where just by the fact that these two vehicles want to go to different places and they cannot just, basically just drive around because they will result in collision, right? They are somehow gonna interact in order to maneuver safely in this intersection, right? This is a canonical example. The third one is that, well, we want to model multimodal distributions, we want to model interactions, that's all great. But at the end of the day, we need to make our decisions in a fraction of a second because our reaction time is fundamental for safety, right? So the question is really how we can model this, have these very complex models, but at the same time, do inference, in a fraction of a second. So that's actually pretty difficult as well. Well, so let's look a little bit at, if we fast forward right from 2017-18, I was mentioning before, to what we've seen in the literature. So in particular, as it comes to motion forecasting, which is also called prediction, we've seen that a lot of papers have been written in modeling a distribution, right, of multimodal futures for every actor independently, right, as a marginal distribution. And that's actually not great. Sorry, my computer is keeping a slide. So, and in particular, we've seen in related work a few versions of how to do this. So whether you model the output as a mixture of Gaussians, right? That's one way to model multimodal distributions. You can model also with occupancy representations. And this is a representation that I personally really like. And there is a lot of work from the lab on this. You can do it as a non-parametric distribution where you can think of trajectories for every actor and then you just model the score or probability for every one of these trajectories. Or you can have multimodality just by the virtue of sampling the initial state and then unrolling these initial states in for example, autoregressive model. Okay, so this kind of, there's a lot of literature, as I say, on this. And you can think of these methods are trading off expressivity for the complexity in time and memory of the representations and the methodology. So in this case, this is very memory expensive as an example. Now, if you think about what these methods are doing, right? So they're modeling a multimodal distribution for every actor. That is representing the marginal distribution of its trajectories. Now, let's look at an example of what might happen in a scene. So if you model the marginal distribution and you're going to utilize this for motion planning, it's actually quite problematic. And let me explain this with an illustration. So here what I'm doing is, this is the self-driving vehicle. We have two actors in the scene. And I'm just drawing samples from the marginal distribution of trajectories for this guy as well as this guy, right? And then you see that you have, plausible explanations of what might happen. But the only thing I have is just individual explanations for every actor. So if you look at the self-driving car, what it's going to do here is, because of all these possibilities, it's going to take a very, very conservative approach for planning if it wants to take into account all these different samples that I did. Right? So this is not going to end with a very, very nice or very good motion planning. However, if you actually look at what really happens in the real world, it's not that every actor is just randomly drawing for its distribution and going ahead, right? It's that in reality, there is not really 4 possibilities. In this scenario, there is like 2 possibilities, right? One is that they are going to jilt me, and then my best plan will be to just continue straight. Right? Or they are not going to jilt to me, and then I need to slow down because otherwise I'm going to get into collision. Right? So this is a much better inference process and thinking about how we should act as a self-driving vehicle given what might happen in the scene. Now, why aren't approaches doing something like this? Is that in order to do this, you need to have a way to very efficiently model the joint distribution about all the actors and then be able to potentially sample from that distribution, right? So coming back to the latency issue, right? So this is actually complicated. So I'm gonna show you one way to do this in a pretty nicely and very, very efficiently. So the way that we're gonna do this is that we are gonna do a system that from raw sensor data, right, to the plan. And in particular, we're gonna first perceive the world. We are gonna be able to learn a model of the joint distribution factors. We're gonna sample from this distribution in a way that is diverse, so that we take into account all this multimodality of the future representations. We're gonna score those scenarios, and then gonna design a motion planner that is able to not be conservative, but utilize all these possibilities of how the future might unroll. Okay, so let's see how we can actually do this, and I'm going to show you new ways to do the prediction part, as well as a new contingency planning that is actually quite nice. Cool. So let's start with perceiving the world. So the way that we're going to do this is the following: is we're going to extract features, right? Again, from in our case, we love this, as I say, versa view representations, and we are also going to utilize high definition maps when we have them. Okay, so in this particular case, we're going to use a rasterized version of the map, because then you have the two representations in the same view. So it's actually something that is it goes nicely, works nicely together. We can also have graph representations of the map, which is some other type of work that we have done as well. All right, so we're gonna pass this information through our favorite, architecture of a neural network. We're gonna fuse the information from the LiDAR as well as the maps, and then we're gonna compute some intermediate feature representations. And then we're gonna use these intermediate representations in order to detect the objects of interest. And in particular here, we're gonna use what is called a two-stage detector, which is end-to-end trainable, right? But this two-stage detector, what it's going to do is it's going to detect the objects of interest. And then instead of just directly output the bounding boxes, we're going to utilize what is called a ROI pooling operation to crop the relevant information aligned with the location and orientation of every one of these vehicles in order to perform better detection, more accurate, as well as better prediction. Okay, so this is actually something that works really nicely versus a one-step detection. All right, so we are gonna extract these feature representations given our detections, and then create some feature information for every one of the actors that we had detected in the scene. Okay. And now the question is, now that we have this representation, how we can actually predict the future nicely. So let's look at how we can create a model where we can sample from this joint distribution. Okay, so we're going to skip one thing that I'm going to show you later. Okay, and you will see why. And then we're going to look at how we can encode the probability distribution of all the actors in a way that we can very, very efficiently sample. Recall that I just mentioned that we have the detections in the scene, and every object detected has a feature representation, right? So we are going to use a sophisticated version of a conditional BAE, and it's conditioned because it's conditioned on the sensors on the map, to create a latent representation of the entire scene. And what is interesting here is that it's a distributed latent representation, so you can handle an arbitrary number of objects. And in particular, we're going to use for encoding and decoding graph neural networks, which are a fantastic tool for learning representations of graph data. And in this case, the graph is across the representations of the different actors in the scene. Okay, so we are going to encode given a graph neural network into our latent representation, and we are going to decode in a deterministic way with another graph neural network. So inference in this model is actually really simple. So we can do feed forward of the network to do detection and create the representations. And we're going to sample from a simple Gaussian. And then we are going to use the graph neural network to create our latent distribution. right? We sample from this, and then basically we use the deterministic decoding to create the representation of the entire scene of how the different actors are going to be moving into the future. Okay, and different samples will create just different entire unrollings of the scene into the future. Okay, so this is the way. So this is a process that you can do very, very efficiently, and it captures through this latent representation the interactions between all the actors in the scene. Okay, so we can do some interesting analysis with this. What I'm doing here is I'm sampling the latent representation twice, and I'm interpolating between these latent representations and then decoding. Okay, this is what you see. So basically between the two extremes, right, which are the two samples, you see that they represent different motions from all the actors, right? And as I interpolate, we have this very nice transition between the different scenarios of how this scene might unroll in the future. Okay, so you see that the model is really capturing nicely all these interactions between actors. So this model, you can actually learn it end to end, including detection. And the way that you do this is you have a supervision for the intermediate representations, in this case, the object detection. So we use a standard cross entropy and smooth L1 for the detection side. And then for the conditional BAE part of the model, we use a combination of a KL loss between the privileged posterior and the prior, right? So that you learn to represent the data, as well as we have reconstruction so that we can train the decoder together as well. Okay, so you can train end to end through this loss function, which is differentiable, and basically obtain the entire representation from the raw sensor data, in this case, all the way to prediction. And this actually works really nicely. These metrics show how well you imitate, in this case, the ground truth, and which are ground truth, trajectories from, in this case, is many thousands of scenarios. And this is how socially compliant your predictions are, which are, if you enroll your predictions into the future, how often do they collide between themselves? This is a notion of whether you're really capturing interactions well. And you see that compared to the state of the art, you end up with much, much better predictions. Now, this type of model achieves great reconstruction. And if you look at, yes, I'm showing here the predictions, as we enroll into the future, right? And the predictions are just shown with different colors and the different time steps of the future time steps. So you see that it works really nicely. And one of the issues here is that it's not using the multimodality very often, right? And while this is great for metrics, it's not necessarily very good for planning, right? Because when we are actually doing self-driving, we care about safety a lot. So what we're going to see next is how can we enhance this model to be able to sample a more diverse set of trajectories in a way that actually they are diverse for the motion planner. So that no matter what the motion planner does, we're always safe with respect to all the realizations of the future. Okay, so let's go into the next step, which is how can we sample these diverse features from this model? So we're going to change the sampling procedure, and we're going to reuse the decoder. Okay, that's the trick that we're going to do. All right, so if you look at sampling base and how I was doing sampling before, but just in general for any of these multimodal representations that people use in the past, so it's very sample inefficient. The samples, in order to get the long tails, which are important for safety, you need to sample a lot of samples, right? And this is gonna basically prevent you from having real-time inference. There has been a couple of approaches recently into how we can encourage diversity, but they are done in a way that they encourage diversity with respect to the trajectories themselves, not for the plans that these trajectories might make our self-driving car do. So as a consequence, if you really want to see all the possible behaviors that your planner might do, you need to sample still a lot of samples. Okay, so let's see how we can enhance this kind of approach. So we're going to learn this diverse sampler, where it's going to be, we're going to sample, so a single draw is we're going to sample K trajectories. Okay, and this, K and roles of the future for all the actors, okay? And we're gonna do this through a, again, graphing enabler, which is one of our favorite tools. And we're gonna learn this to encourage, as I say, diversity, not necessarily only of the trajectories themselves, but their effect on the motion planning, okay? And this will allow us to cover all the features that matter with a very small number of samples, which is what you need for efficiency. The next thing that you need is that since we have changed the sampling procedure, we don't have a good likelihood estimation. So we need to somehow understand how likely a feature is versus another. So the way that you can do this is the following, is that you can learn, in this case, we have a very simple probability representation. And then the way that we learn this is by saying that we want to minimize the KL between our model and the ground truth, where we smooth the ground truth, and it's not as simply delta in the realizations, but it's basically an exponentially decaying function with respect to the ground truth. Okay, and this allows you to learn better than if you have very picky distributions. Cool. And the last bit that we need is, well, now we have a way to have diversity in the samples of the multiple features of the joint distribution of all the actors. So that's great. But we somehow need to come up with a motion planning that is able to ingest this information and use it in a way that is useful for, doing better motion planning than the standard way. So let's see how we can do this. And maybe I should motivate why we need a different type of planner in the first place. So let's look at the scenario like the following, where there is two things that might happen, right? Which is a similar scenario as before. The two actors might yield, right? Or maybe they might decide to actually go into the intersection and then basically cut in front of us, right? So the first one looks more likely, but if you look at the worst case scenario type of planners that we see a lot in the literature, what happens is that you are never going to plan a trajectory that is something like this, right? Because if you take into account all the different things that might happen, you will end up with a collision. Okay, so what happens is that then standard planners or worst case planners result in like super conservative behavior for the self-driving vehicle, and this is what you observe in many of the systems that are available out there. Okay. So you will end up with something that you can handle all possible scenarios, right? You will end up going too slow. So let's look at how we can do something different. So we're going to exploit the fact that our planner, like most planners, is based on model predicted control, where we're going to replan at every point in time that the new information is available, typically 100 milliseconds. Okay, and if you think of this situation, or the typical motion planners plan a trajectory of, say, multiple seconds, right? Typically 8 seconds or so. You only execute the beginning, right? So what we can do is make sure that we have the right short-term decision, and we're going to postpone what to do after to later as we acquire more and more evidence. And what we need to do with this contingency planning is to come up with a short-term decision such that no matter what happens in the future, we can handle it safely. Okay, so this is the core of the idea of this contingency plan. Okay, so let me very quickly go into how this works, and then I will show you some results. So we're going to sample multiple short-term trajectories, as you see here, and then we're going to sample, oops, and my computer doesn't want to work anymore. Cool. And then we're going to sample multiple long-term trajectories for every short-term trajectory, right? And the idea is to decide between these short-term trajectories which one should be the best. Okay, so let's see how we can cost this kind of planning. Cool. So as I said before, is that we want to execute this short-term maneuver that is safe, even in the worst case. And we're going to use the following. So for the short-term trajectory, we're going to use a worst-case approach, right? We say that for this short-term thing just in front of us, we will take the action such that we are safe among all the possibilities that might happen. Okay, and this makes sense, right? We want to make sure that we don't arrive to a collision. And what is different, right, that you will observe with traditional planners is that that will be also worst case, right? But instead here, we're gonna have a particular cost to go where we're gonna sample from the realizations of the future. And we're gonna cost the cost to go in a way that the cost is the best cost with respect to the trajectory. So the trajectory, you pick the trajectory with the minimum cost for that particular realization of the future, and then you weight it by the probability of that happening. And this is sort of the definition of the cost to go. Okay, and this is your sort of contingency planning where you don't need to decide what to do with respect to all those different futures, right? It's not a single trajectory, it's multiple ones. But you decide on a single trajectory for the immediate future. Okay, and your cost, you can use your standard definition, safety, progress, comfort, your favorite sort of costs. Cool. So what does this do is that, so here's a scenario with the two vehicles, right? And a difficult intersection. This is, so imagine that we decide to cruise and continue, at current speed, right? So this is the short-term trajectory and all the possible long-term trajectories, right? So let's look at whether this is actually a good short-term trajectory. So if what happens is something like this, right? This, that they give to us, this will be a good short-term trajectory. But if they decide to not give to us, then we will need to slam on the brakes, right? So this is going to be very costly in the cost to go. So this is not going to be a trajectory that we select, right? It's unsafe. Instead, if we look at, for example, let's slow down a little bit, to prevent maybe the future. Then what happens here is that if they yield to us, we can always accelerate, right? As we gather more evidence, so that's, we can actually very, very well realize the future. And if they decide to cut in front of us, we can actually react in a much safer manner without this hash brake. So this has a much smaller cost to go. So this will be a much better trajectory. Right? So you end up with this behavior that is not too conservative, but you are safe. Cool. So we're going to evaluate this now in a closed loop simulator, which is an end-to-end closed loop simulator with sensor sim, which is one of the great tools that I guess we have in the lab. And we're going to see how this works. Okay. So these are the metrics I'm going to show. In this case, this is
just a small comment that we are running out of time. So
yeah, sorry, I have one more slide and I'm done. Yeah.
Okay.
So in this case, you see that you have small collisions. You reduce considerably the amount of collisions. You progress more towards the goal. You have less jerk. And we have more lateral acceleration because you end up with this, changing lanes and other behaviors that are actually good behaviors to have. They are safer to have. Okay, so this results in a much better plan. Cool. So let me just show you a bit of the video and then I change.
Green, and the other vehicles and their trajectories in blue.
Can you hear this?
And finally, the pedestrians in pink.
Yes, we can.
On the diverse predictions and response from the planner. The short-term action planned in the SCB is plotted in black, and the contingent trajectories are plotted in different colors, which in this case accounts for the variations in the speed profile of the left turning car. As you can see, the SCB passes the intersection safely and cruises smoothly. In this scenario, the SCB plans different accelerating trajectories to be safe to unlikely samples from oncoming traffic coming into our lane and successfully goes across the intersection. Here, our model.
Cool. So I'm going to stop there just in the interest of time. And just to conclude, right, so I show how to model the joint distribution that allows to do reasoning about distinct features, how we can cover all the possible features with a small amount of samples so that we are very efficient, and how we can build a motion planner that can be less conservative, but very safe in handling these difficult situations. Thank you.
Thanks a lot, Raquel.